Imagine standing at the edge of a cliff you cannot see. Below you, there is no ground, no bottom, just an absence so complete that even light itself cannot climb back out. You take one step forward, and in that moment, every law you've ever trusted begins to bend. This is not a metaphor. This is a black hole. And the question we're asking today is deceptively simple. When something falls in, does it truly disappear? The answer will take us to the edge of physics itself. Black holes are not holes. They are objects, incredibly dense, unimaginably massive objects that warp the fabric of space-time around them. According to Einstein's general relativity, mass curves space. The more mass you pack into a smaller volume, the steeper that curve becomes. A black hole is what happens when that curvature becomes infinite. At the center lies the singularity, a point where density climbs beyond comprehension, where the equations break down and produce infinities we cannot interpret. But we never see the singularity directly. It is hidden behind something far more mysterious. The event horizon. This is the boundary. Not a surface you can touch, not a wall, just a line in space-time beyond which escape becomes impossible. Once you cross it, every direction you might try to move leads inward. The future itself points toward the singularity. And light. Light cannot outrun this geometry. It is trapped, not by force, but by the shape of space itself. This is why black holes are black. So what happens when matter crosses that line? Let's follow an object, a probe, a star, even a single atom. As it approaches the event horizon, something strange occurs. Time begins to shift. From our perspective, watching from a safe distance, the object appears to slow down. Its motion stretches. Its light red shifts into deeper and deeper wavelengths until it fades entirely. We never actually see it cross. To us, external observers, the object seems frozen at the edge, asymptotically approaching the horizon, but never quite reaching it. Time dilation, predicted by relativity, means that the closer something gets to the event horizon, the slower its clock appears to tick relative to ours. But here's the unsettling part. From the object's own perspective, nothing unusual happens. Its clock ticks normally. It crosses the event horizon in finite time. It continues falling. There's no barrier, no sensation of crossing a threshold. It simply goes in. And once it does, there is no coming back. But does it disappear? Not immediately. Not in the way we might think. The matter continues to exist inside the black hole. It falls toward the singularity, stretched and compressed by tidal forces, so extreme that atomic bonds snap, particles are torn apart, and everything is reduced to its most fundamental components. But the information about that matter, the quantum states, the properties, the history, should, in principle, still exist. Physics has a rule about this. Information cannot be destroyed. It can be scrambled, hidden, encrypted into chaos, but not erased. This is where the trouble begins. In the 1970s, Stephen Hawking made a discovery that shook the foundations of theoretical physics. He showed that black holes are not entirely black. Quantum effects near the event horizon cause black holes to emit faint thermal radiation. This radiation, now called Hawking radiation, is so weak that we have never detected it. But theoretically, it means black holes lose mass over time, very slowly. A stellar mass black hole would take longer than the current age of the universe to evaporate completely. But given enough time, trillions upon trillions of years, every black hole would shrink, dim, and eventually vanish. And here is the paradox. If a black hole evaporates, what happens to the information of everything that fell inside? Hawking radiation is thermal. It carries no memory, no structure, no trace of what the black hole consumed. If the black hole disappears entirely, and the radiation it emitted contains no information, then the information is gone. But quantum mechanics forbids this. Information must be preserved. Always. This is the black hole information paradox, a direct conflict between general relativity and quantum mechanics. Two of the most successful theories in physics contradicting each other at the most fundamental level. For decades, physicists have searched for a resolution. Some believe the information is never truly lost. It might be encoded in subtle correlations within the Hawking radiation itself, invisible at first, but recoverable in principle. This idea gained traction with the development of the Page curve, a mathematical framework showing how information might gradually leak out as a black hole evaporates. Others turn to the holographic principle. This radical idea suggests that all the information about the three-dimensional interior of a black hole is encoded on its two-dimensional event horizon. Like a hologram, the surface contains everything. If this is true, then perhaps the inside is not as separate as we thought. Perhaps the distinction between inside and outside is an illusion. Then there is the concept of soft hair. Proposed by Hawking himself near the end of his life, it suggests that information might be stored in quantum properties on the event horizon, subtle imprints left by infalling matter. These quantum hairs would not prevent the black hole from appearing smooth and featureless from a distance, but they would carry information nonetheless. None of these solutions are proven. They are elegant. They are mathematically compelling. But we don't yet know which, if any, is correct. So let's return to the question. Do objects truly disappear inside black holes? The answer depends on what we mean by disappear. If we mean, do they cease to exist immediately upon crossing the event horizon? No. The matter continues falling. It is stretched, torn, and compressed, but it persists, at least for a time. If we mean, can we ever retrieve that matter, or the information it carried? Probably not. The event horizon is a one-way boundary. Nothing that crosses it can return. But if we mean, is the information destroyed forever? Science says no. Physics demands that information is preserved, even if we do not yet understand the mechanism. The black hole might evaporate. The information might be encoded in radiation. It might be imprinted on the horizon. It might exist in a form we have not yet imagined. But it does not simply vanish into nothingness. Black holes are not erasers. They are encryptions, locks with no visible keys, puzzles written in the deepest language of the universe. And perhaps that is what makes them so unsettling. They are not just objects in space. They are questions the universe poses to itself. What happens when matter meets its ultimate limit? What does it mean for something to exist beyond reach? And how do we reconcile the two greatest theories we have when they refuse to agree? We do not have final answers yet. We may not for a long time. But the search itself has already taught us something profound. The universe does not erase. It transforms, it hides, it encrypts, but it remembers. And somewhere, in the quantum hum of an evaporating black hole, in the geometry of a curved horizon, in the mathematics we have yet to fully decode, the information remains.